Okay, so today I am going to talk about rate laws, how to write rate laws and how to calculate for rate law. The relationship between the rate of reaction and the concentration of one reactant is determined experimentally by keeping the concentrations of other reactants and the temperature constant. So for example, what that means is if you've got A plus B yields C, or even C plus D, or whatever the products are, it doesn't matter, because the concentration of the products doesn't have any effect on the reaction rate, right? Reaction rate is only determined by factors concerning the reactants. So if you want to find out how the concentration of A affects the rate of the reaction, you're going to want to keep B constant and the temperature constant, and then you'll change the concentration of A and see how the reaction rate changes based on that. So reaction rate is measured for various concentrations of the reactant in question. Again, you have to keep the concentration of all the other reactants constant along with temperature, and then you play around with the concentration of the reactant and then look at how that affects the rate. As an example, hydrogen gas reacts with nitrogen monoxide gas at a constant volume and at an elevated constant temperature according to this equation. So 2H2 plus 2NO yield N2 plus 2H2O. This means you have 4 moles of reactant gases that react to produce 3 moles of gaseous products. The result is, as the reaction proceeds, the pressure of the system will decrease, and you can use that to measure reaction rate based on how quickly the pressure decreases. So all of this is done through experimentation. Suppose we have a series of experiments by using the same initial concentration of nitrogen monoxide, right? So we're going to keep NO constant, but we're going to change the initial concentrations of hydrogen gas. The initial reaction rate is going to vary directly with the concentration of hydrogen. So for example, if in our imaginary experiment, we double the concentration of hydrogen gas, that results in doubling the rate of the reaction. If we use the letter R to represent reaction rate, and we use the square brackets, which represents molarity. So don't forget, square brackets is molarity, which is moles per liter. We can write a relationship between concentration and reaction rate like this. So the reaction rate is proportional to, and that font is kind of weird, proportional to the concentration of hydrogen gas in moles per liter. Suppose then we change and we keep the concentration of hydrogen constant, but we're going to vary the amount of nitrogen gas. So we're going to do the same thing, but we're going to switch the reactant. So we're going to keep hydrogen gas constant, and we're going to vary the concentration of nitrogen monoxide. Based on our imaginary experiment, you would go through, read the pressure, and then determine the initial rate increase is 4-fold when the concentration of NO is doubled. And when you triple the concentration of NO, you increase the reaction rate by 9. So that kind of that relationship is a square. Reaction rate varies with the square of concentration. When you double NO, reaction rate times 4, triple NO, reaction rate times 9. So we would write the reaction rate is proportional to the concentration of NO squared. Because R is proportional to the concentration of hydrogen and the square of the concentration of nitrogen monoxide, it will also be proportional to their product. So we can rewrite our expression as R is proportional to the concentration of hydrogen times the square of the concentration of nitrogen monoxide. Now, if we want to change the proportionality to an equality, we introduce a proportionality constant, K, and we change it to R equals K times the concentration or the molarity of H2 times the square of the molarity of NO. This is called a rate law. It is an equation that relates reaction rate to the concentrations of reactions. It can be used for a specific reaction at a given temperature. Increasing the temperature will increase the reaction rate of most reactions. That's what I talked about last week. It's one of the 5 factors that affect reaction rate. The value of K, therefore, usually increases as temperature increases. But the relationship between the reaction rate and concentration almost always remains unchanged. So if you increase the temperature, you only affect the proportionality constant, K, not the relationship between rate and concentration. So the general formula for rate law is R equals K times A to the N times B to the M. Now, these are obviously just variables. So R is reaction rate, K is the specific rate constant, A and B are concentration of reactants, N and M are the powers to which the concentrations are raised. And the way that you determine what N and M are going to be is by looking at experimental data. And that's what I want to do mostly today. Now, the power to which the reactant is raised is called the order of the reaction. So for example, the value of N is the order of the reaction with respect to A, because it's A to the N. Again, I'll just write the rate law. K times A, oh, that's a terrible bracket, to the N times B to the M. So you talk about the order of N with respect to A. So the reaction is the nth order in A, or the mth order in B. Again, N and M are going to be numbers. So if N is equal to 1, then you would say the reaction is the first order with respect to A. And if M is 2, you would say the second order in B. N and M are usually small integers or 0. I would guess you'd probably see 0, 1, or 2. Those would be the only ones. I rarely see 0. So your orders are going to be either 1 or 2. Now the order of 1 means that the reaction rate is directly proportional to the concentration of the reactant. That's what we saw with hydrogen gas. If you double hydrogen gas, you double reaction rate. If you triple hydrogen gas, you triple reaction rate. That's a first order. An order of 2 means that R is directly proportional to the square of the reactant. That's what we saw with nitrogen monoxide. If you double NO, you quadruple the reaction rate. If you triple NO, you increase reaction rate by 9. If you have a 0 order, it means that the reaction rate doesn't depend on the concentration of the reactant at all, as long as some of the reaction is present. The reactant, not reaction. But like I said, it's very rare that you'll see an order of 0. Now, every reaction has an overall order, and that's going to be the sum of all of the reactant orders. So it would be N plus M. Orders in a rate law may or may not match the coefficients in a balanced equation. It has to be determined by experimental data. Sometimes it will match the coefficient, sometimes it won't. Now, about the specific rate constant, which is K, it's a proportionality constant that relates the rate of the reaction to the concentrations of the reactants. Now, there's 6 things that we can say about K. Once the reaction orders are known, the value of K must be determined from experimental data. And this is the main thing I want to go over a few examples of this. So the first thing you have to do is to determine the orders of the reactants. Then you use one of the trials in the experiment. You use that data to calculate K. The value of K is for a specific reaction. It also depends on the overall order. It does not change for different concentrations of reactants or products. It is also for a specific temperature. If you increase temperature, you increase K. And the value of K becomes larger with a catalyst. So let's look at an example of how we do this. 3 experiments that have identical conditions were performed to measure the initial rate of the reaction. 2 hydrogen iodide will yield 1 hydrogen gas plus 1 iodine gas. So our experimental results are as follows. So when we have a concentration of, that's the wrong thing, concentration of hydrogen iodide as 0.015, the reaction rate is 1.1 times 10 minus 3. When it becomes 0.03, the rate becomes 4.4 times 10 minus 3. And when we triple the concentration to 0.045, we increase the rate to 9. So 2 things I'm going to ask you to do in this topic. 1 is to write a rate law. 2 is to find the orders. And 3 is going to find K. So first thing, we have to figure out what the orders are. So we know that the, let me write the equation again, 2HI yields H2 plus I2. So we know that the rate law, because there's only 1 reactant. Again, rate laws have nothing to do with products because reaction rate is not determined by products at all. It's all about the reactant. So reaction rate is equal to K times the concentration of HI to the N. And we're going to find the ratio of the reactant concentrations between experiments 1 and 2. And we're going to see how the ratio of concentration affects the ratio of rates between reaction 2 and reaction 3. Actually, instead of doing that, I'm just going to go back here and explain it. So I'm going to look at what happened between 1 and 2 and what happened between 1 and 3. So between reaction 1 and reaction 2, we doubled the concentration, right? 15 to 30. I'm going to ignore the decimals, 15 to 30. The rate went from looking at the exponents all the same. I'm just going to look at the integer in the front, 1.1 to 4.4. So between these 2, we multiply by 2, this times 4. That should already tell you where we're going because it is not a direct proportion, which means the order is not equal to 1. But just to double check, I'm going to look at between 1 and 3. That's times 3. Here between 1 and 3, that's a factor of 9. So that means that, N is equal to 2. It's a square. So if I go back here again, we've got rate is equal to K times HI squared. Now, in order to find K, I'm going to take any one of these 3 data because I've got the concentration of HI, which is here, and I have rate, which is here, and I'm going to solve for K. So I'll rearrange the equation, rate over HI squared, and pick any one you want. It doesn't matter. Any one of the 3 experiments, the data should equal the same. K is equal to, I'll just take number 1, 1.1 times 10 minus 3 over 0.015 squared, excuse me. And find my calculator. So we have 1.1 times 10 minus 3 divided by 0.015 squared, and you get 4.9. That's the specific rate constant. Yep, 4.9. Okay, here's another one. Yeah.
How to know value of n?
Oh, how to know the value of n? Okay, so that's what I did over here. So I looked at between experiment 1 and experiment 2, what did I do to the concentration of hydrogen iodide? From 0.015 to 0.030, I doubled it, right? Because 0.030 is 2 times 0.015. So if I double HI, what is the result of reaction rate? It's times 4, because it goes from 1.1 times 10 minus 3 to 4.4 times 10 minus 3. So if I double HI, the rate increases by 4. That is a square proportionality. But just to double check, I'm going to compare experiment 1 to experiment 3. So from 0.015 to 0.045, that's times 3. I've tripled the concentration. What happened to the reaction rate between experiment 1 and experiment 3? It's times 9. So if you triple HI, you increase reaction rate by 9. That confirms that N is equal to 2. It's a square proportionality. Does that make sense?
Yes.
Okay. So once I figure out the order, then I've got all of this data for hydrogen iodide concentration, which is here. I've got all this data for rate. So you just pick one of the 3. I just chose the first experiment. So I used the concentration of 0.015 here and a rate of 1.1. I could have taken experiment 2 or 3. It doesn't matter, but you just take the concentration and the rate from any of the 3 to calculate K. Okay, here's a different one, but now we have A and B. So we're going to have to calculate for A, and we're going to have to calculate the order. We're going to have to calculate the order for A and the order for B. Now, the way that you have to do this is, again, you have to, if you want to look at the effect of changing the concentration of A, you have to pick the 2 experiments where B is constant, but A changes. And then look at how changing the concentration of A affects the rate. So if I want to, first I'm going to write the rate law. Always start with writing the rate law first. So R is equal to K times A to the N times B to the M. Now, in order to find N, again, I need to find 2 experiments where B is constant, but A changes, and compare those 2 experiments. So that would be experiment number 1 and number 3. Because for number 1 and number 3, B doesn't change, but A does. So I'm going to compare for experiment number 1 and experiment number 3. For experiment number 1, I went from 1.2 to 3.6. That's a value of 3. I tripled the concentration. What did I do to the rate? 8 times 10 minus 8 increased to 7.2 times 10 to the minus 7. Now, if you're not sure what that relationship is because your arithmetic skills are not strong, use your calculator. 7.2 times 10 to the minus 7 divided by 8 times 10 to the minus 8. That is a value of 9. So that means, oops, I'm totally doing that wrong. A times 3 rate. Oh, no, I was doing that right. Oh my goodness. Did not set that up properly at all. Sorry. Okay, so for A, experiment 1, we have concentration of A times 3, rate times 9. Never mind experiment 1. Because we're comparing 1 and 3. I hope that makes sense. I'm like, my brain doesn't work so well this morning. So I'm just looking at these two versus these two. What's the relationship? So from 1 to 3, we increased it by 3. The rate jumped up to times 9. So that is an order of 2. So now I can rewrite my rate law A squared. Now for B, I need to look at 2 experiments where A doesn't change, but B does. And that would be experiment 1 and 2, because here you see A stays the same. So for B, the concentration of B decreased by 2, or let me say decreased by half. And what happened here? From 8 times 10 minus 8 to 4 times 10 minus 8. That is also 1/2. So that means my order of B is 1. So that's my rate law. R equals K times A squared times B. And the last thing you do is you just pick one of the 3 experiments, plug in your values for A, B, and the rate to calculate K. So let's change to green, I guess. So rearranging, I like to rearrange first so that I've got everything where I need it. A squared times B. Again, I'll just go with experiment number 1 because that's just easiest. So the rate is 8.0 times 10 minus 8 divided by 1.2 squared times 2.4. And what is that? 8 times 10 minus 8 divided by 1.2 squared times 2.4. And I get 2.3 times 10 minus 8. All right. Double check that. 8 times 10 minus 8 divided by 1.2 squared times 2.4. Yep, 2.3 times 10 minus 8. I hope that makes sense. Yep, 2.3 times 10 minus 8, there it is. Yep. Let's do one more. Let me find. Oh, I don't have one. Hold on. Let me find another example. Chemistry, kinetics worksheet. Waiting for Microsoft Often to open. haven't heard anything from the teachers line group, so I don't know what's going to happen. All right, let me transfer this data first. Wait, see if I can share that. Give me a sec. No, I want to share. My AirDrop is not on. Turn that on. iPad. Can you go to Notability? Nope, doesn't want to work. No, I want a different note. Oh, I guess it was already open. All right. Almost there. Share screen. AirPlay. Huh? Seriously. Oh, it says I need to plug in. Okay. Zoom. There we go. All right. Here we are. Okay, so here I've got my data for 3x plus 2y yields z, and I've got 3 experiments, so I can look at the data. Again, first thing we want to write the rate law. So r equals k times x to the n, y to the m. I want to find n and m first. So I want to look at for figuring out the order of x, I need to pick experiments 1 and 3, because that's when y is constant, but x changes. Now, this is an interesting one. After I told you, you probably wouldn't see 0. This is hilarious. So if you look at what happened to x, the concentration, we doubled it, but the rate stayed the same. That is an indication of an order of 0. So if you answer question A, what is the order of reactant X? It is 0, because when you double X, literally nothing happened to the rate. So the rate doesn't change based on the concentration of X, as long as X is there in any amount. Now, what is the order of reactant Y? That is calculating M for Y. So I'm going to look at experiments 1 and 2, because for experiments 1 and 2, X stays the same, but we change Y, and we do see that rate changes. So what did we do to Y? We cut it in half. What happened to rate? It decreased by 1/4. Again, the 2 to 4 is a square. So the order of reactant Y is 2. The overall order is going to be the sum of all of the orders. So 2 plus 0 is 2. And so the rate law becomes R equals K times X to the 0, or you could just write 1 if you wanted to, or just keep it out of it, but just to take baby steps. And then it's Y squared. So you could rewrite that R equals K times Y squared, because this is basically equal to 1. And then find the value of the rate constant. Again, pick one of the 3 one of the 3 experiments and fill in your values. The nice thing is that you don't have to worry about X at all. So again, I'll just take experiment number 1. Solving for K, R over concentration of Y squared. So that's equal to 4 divided by 0.2 squared. And that's 100. Bink. I honestly don't care about units, because I'm assuming you guys all know how to cancel units if you actually needed it in there. So I hope that made sense. Again, remember that